So this is sampling distribution, unit 5, and we're your teachers, Sajid Rahman, and I'll cover topics 5.3, 5.5, and 5.7.
Hi, I'm Shomit Mian, and I'll be covering topics 5.1, 5.2, and 5.4 for sampling distribution. So, let's get into it. Okay, so let's start off with a quick tune now. Suppose that you are the head of a chocolate chip cookie factory. Your company's claim is that each cookie has a 10% chance of getting 3 chocolate chips in one cookie. To test this claim, you select 50 cookies out of a freshly made batch of 2,000 cookies and note down the number of chocolate chips in each cookie, repeating this procedure 100 times. Throughout your research, you notice that no two samples are identical. Now, why is this? You can pause the video for a moment to try and figure it out. But the answer is because of something called sampling variability. Sampling variability is defined as how much an estimate varies between samples. Since sampling variability refers to the variation between samples, increasing or decreasing a sample size can lead to change in its variability. For example, let's look at the do now again. A sample size of 50 out of the population of 2,000 would very likely give different results than if we were to use a sample size of 500 out of the same cookie population. There would be less room for sampling variability to arise, and therefore the samples would likely be more close together. Now let's discuss the normal distribution. The normal distribution is one particular symmetric unimodal distribution used to describe the distribution of a normal random variable. The normal distribution curve, as shown below, is bell-shaped and symmetric and has an infinite base. The mean of the distribution is located at the center. Since we want a unit of measurement that's consistent between all normal distributions, we chose to use a unit that arises naturally out of the curve's shape, which is the standard deviation. The standard deviation measures its spread. The standard deviation can give an approximation to the amount of data in a specific location on the curve, as approximately as shown in the diagram. 68% of the area falls within one standard deviation of the mean, approximately 95% of the area falls within 2 standard deviations of the mean, and approximately 99.7% of the area falls within 3 standard deviations of the mean. We can calculate the areas under a normal curve using calculator functions. On the calculator, the function normal CDF with the parameters lower bound, upper bound, mean, and standard deviation give the area between two values and calculates the probability of a data point falling into that range, while the function inverse norm with parameters area, mean, and standard deviation does the opposite. It gives the z-score with the given area to its left. These functions can be accessed by pressing second vars and then either normal CDF or inverse norm on the calculator. So now let's look at an example problem. The player base of a certain video game has an average of 1,500 coins and a standard deviation of 100 coins. What is the probability that someone who plays this game has less than 1,370 coins? You can take a moment to pause the video to figure it out. Be sure to use your calculator's normal CDF function for this. Okay, let's look at the answer. So by using normal CDF with a really small lower bound, the upper bound as 1,370 coins the mean as 1,500 coins, and the standard deviation of 100 coins, we will find that the probability is 0.0968.
Central limit theorem, topic 5.3. So with this central limit theorem, there are three conditions. And also the central limit theorem typically works when you deal with sample means. So moving on, back to it, the three conditions. One, a random sample mentioned. So in the problem, you have to make sure that it says that a random sample was selected, and this basically just ensures that you get accurate results in the study or experiment. The second condition is a 10% condition, and this is where the sample size has to be less than 10% of the total population, and this proves independence between the samples. So it's not dependent on other samples or outside factors. And then the third condition is n is greater than 30. So this basically is just where the sample size is larger than 30, and it helps predict the sample distribution behavior based on the parent population distribution. So the meaning behind these conditions. So the central limit theorem states that given the necessary conditions that those last three things are met and satisfied, that one, the set of all sample means is approximately normal, which is by that third rule. The mean of each set of sample means equals mu, the mean of the population. And I'll explain this in a little bit. And then the third one, the standard deviation for each set of sample means is equal to the standard deviation over the square root of n. So, like this basically is just the standard deviation of the parent population divided by the square root of the sample size. So let's move on to an example problem. You can pause it and try this on your own, but I'll continue on with the answer. So let's say that a student was calling 100 people in New York City and leaving them on hold, recording how long they would wait until they would hang up. According to the New York City census, the distribution for this wait time is skewed right. How would the sample distribution behave? So again, you could pause it and answer it on your own, but here's the answer. The distribution for the sample would be normal because the sample size is 100, and this satisfies the third condition of central limit theorem. So a note from this is that a distribution for the sample would always be normal regardless whether the parent population distribution was skewed or not. So it could have been skewed right, left, or be normal. But since the sample size was greater than 30, that indicates that it is large and will always be normal. Example problem 2. So this is basically the same problem, except before the sample size was 100 people and now it's 10 people, so just note that. So let's move on. Let's say that a student was calling 10 people in New York City and leaving them on hold, recording how long they would wait until they would hang up. According to the New York City census, the distribution for this wait time is skewed right. How would the sample distribution behave? Again, you could pause and answer on your own, but here we go. So the distribution for the sample would also be skewed right because the sample size is 10 and this does not satisfy the third condition of CLT.
Hey, it's me, Shomit, again. And let's take a look at lesson 5.4, biased and unbiased point estimates. So, in the context of sampling distributions, bias means that the sampling distribution is not centered on the population parameter. Therefore, the sampling distribution of all sample proportions and means are unbiased, meaning that for a given sample size, they are centered at the population proportion or mean. We know this is true because of the central limit theorem that we have just discussed. Let's take a look at this diagram, which shows an example of an unbiased and a biased distribution. The unbiased distribution is shown in black, while the biased distribution is shown in blue. The unbiased distribution is centered on the estimated parameter, while the biased distribution is not.
Hello, it's me again, and we will be going over sampler proportions, topic 5.5, and I think the best way to learn is by going through an example. So example, according to the New York City Census, 87% of adults of age 20 and above are able to drive. A student wanted to put this to the test and took a random sample of 200 adults within the specified age range, which is, as mentioned, 20 and above. What is the probability that the proportion of people in the sample with the ability to drive is less than 85%? You can pause, solve it on your own, or try to at least, but I'll be moving on. Step 1. Check conditions. The first condition is to make sure that a random sample was mentioned, and it was, and this basically ensures accurate results in the study. Then the second condition is to make sure that the sample size is less than 10% of total populations, and in this case 200 adults is less than 10% of the total population of adults in NYC, and this ensures independence in the sample. And then the third condition is the success and failure condition. And you might recognize other two conditions from the central limit theorem, but this third one is different, and because the third one in central limit theorem was to make sure the sample size was greater than 30, but that's not the case for here. And like that third condition from central limit theorem, the success and failure condition also ensures a normal distribution approximately. But unlike the CLT, this involves a few equations, such as NP being greater than or equal to 10. So N is the sample size and P is the probability of success. So 200, which was mentioned before as the sample size, and the probability of success, 0.87, was also mentioned before. So 200 times 0.87 is 174, and that is above 10, so that's satisfied. And then the second part is NQ, which is sample size times the probability of failure. And to find that, you just do 1 minus P, which is 0.87, and 1 minus 0.87 is 0.13. So 200 times 0.13 is 26, and that's also above 10. So all three of these conditions are satisfied and met. Moving on to step 2, finding the mean and standard deviations. And remember, these values of mean and standard deviation are for the sample proportions, not the parent population. So the mu of the sample proportion is equal to the probability of success, and the probability of success is 0.87. So that means the mu of the sample proportion is equal to 0.87. Then the second step, standard deviation of the sample proportion, and this is equal to the square root of probability of success times the probability of failure divided by sample size. And that is the square root of 0.87 times 0.13 over 200, which is equal to 0.0238. And that means the standard deviation of the sample proportion is 0.0238. Moving on, step 3, solving the problem at last. So with this, the easiest way to do this is with a calculator to use normal CDF to find the probability that the proportion of adults that can drive in the sample is less than 85%. So to use normal CDF, you press on your graphing calculator, second, vars 2, or normal CDF, and then you input some data. So it should look like this, normal CDF in parentheses 0, 0.85, 0.87, 0.0238, and parentheses. So I'll go over what these values are. So 0 is the lower bound, the minimum value. 0.85 is the upper bound, which is the maximum value because you're trying to find the probability that the proportion of adults that can drive in the sample is less than 85%, not above it. Then C, you find you put the average, which is 0.87 that you solved before, the average for the sample proportion, and then the standard deviation for the sample proportion, which is 0.0238. So, and this is basically uh, probability notation, which is the probability that the sample proportion is less than 0.85. And if you do this correctly and put it in your calculator, you should get 0.20. So therefore, there is a 20% probability that less than 85% of the people in the sample are able to drive. Hello, it's me again. So sample means topic 5.7. So this is where you use the central limit theorem, unlike the last problem. And I think the easiest way to learn this is by going through a problem once again. So example, a student wants to survey his school to see how long their wooden pencils would be after a month. Their target length for each pencil is 2 inches long after the observation period. The distribution of length is skewed to the right with a mean of 2 inches and a standard deviation of 0.5 inches. The student wants to check this and take a random sample of 100 pencils, each from a different student, and calculates the mean length of each. What is the probability that the mean length in the sample of 100 pencils is within 0.1 inches of the target length? Okay, so you can pause it, try it on your own, or you can just follow and learn and do it with me. So the first step is to check conditions. So when dealing with samples mean, you use the central limit theorem as I mentioned before. And the first condition you check is to make sure that a random sample was mentioned, and in this case it was. Then you check that 100 pencils is less than 10% of the total pencils in the school, and that's obviously the case. And this is to assume independence. And then the third condition is 100 pencils is greater than 30. And this indicates that the sample is normally distributed because it's large. Then step 2, finding the mean and standard deviation of the sample means. Okay, so the first step is that the mu of the sample average is equal to mu as well. So before you see that mu is 2 inches, so the sample mean is also 2 inches. Then there's a formula for standard deviation of sample means too, which is a standard deviation of the population over the square root of n. And that's the standard deviation of population over square root of n is basically 0.5 inches over the square root of 100, which is 10. So 0.5 inches over 10 is 0.05 inches. So this standard deviation of the sample means is 0.05 inches. Then step 3, you solve the problem. And this picture here is basically a normal distribution uh, graph, and it shows the relationship between average and standard deviations and the percentage of data like about the mean of each standard deviation and what they contain. Like one standard deviation away from the mean contains 68.2% of the data, two standard deviations is 95.4%, and three standard deviations about the mean is 99.7% of the data. And let's continue. So the sample means and the target length is 2 inches and the standard deviation is 0.05 inches as you solved in the second step. Then the problem asks for the probability that a pencil length would be within 0.1 inches about it. So that's 0.1 inches above or below. And then for this to happen, you would need to add or subtract two standard deviations from the mean, because one standard deviation is 0.05 above it or below it, and two is 0.1 above or below it, which is what the question asks. And then uh, this is basically the same thing. Two standard deviations about the mean is 95% of the data, or more accurate, 95.4% of the data.